So that motivates, in part, these propensity score methods. And when I say propensity score, what I mean is just the probability that somebody who looks like X would have been treated. So it's the probability that A equals A given that X equals little x. And I'll use this notation pi of little a of X to notate that. And this is a function of X. So if, in different strata of the population, different proportions of people are being treated. So another way to think about this is what is in this stratum of the population, what's the proportion of people who are treated? So different strata have different proportions. So it is a function of X. To give you an example, the propensity score in a randomized trial, if the exposure is a coin flip with 50-50 chance, then no matter what the value of X is, in every stratum of the population, it's 50-50. So pi a of X is equal to just 0.5 for all X. This is also, by the way, a conditional mean, because I can write this as the conditional mean of A, indicator of A equals A, given X. So it's a conditional expectation, as well as a probability, because A is a binary variable. So why is this thing useful? Well, it turns out that the propensity score summarizes all of the confounders into a single number. So in terms of a DAG, you may look at it like this. We have YA and A, and we're assuming that all these X's are all of the confounders. There's nothing else that impacts both of these. So if I draw this DAG, I am implying that there is nothing else. And that means that if I condition on all of these X's, then A and YA are indeed conditionally independent. What I'm trying to show here is that actually, if I just condition on the propensity score as a function of X, so here I'm just writing X, but it would be X1, X2, X3, so on and so forth, because I'm conditioning on all of those. I don't actually have to condition on all of these individually. I just have to condition on the propensity score, taking a particular value, which is very interesting. And so so this is how you write it in DAGs. Mathematically, this is the statement. If the potential outcomes are independent of the exposure given the covariates, then the potential outcomes are independent of the exposure given the propensity score, this particular function of the covariates. So this is nice because these covariates, there could be x1, x2, x3, x4, so on and so forth. So you have to condition on 10, 20, 30 different things. But down here, this is just a single variable. It's a one number summary of all of the covariates, and you just have to condition on that one number. So a little proof of that, you can skip ahead. This is not required if you're not interested. But the basic idea is that you use this. This is the conditional independence that we have, right? If A is conditionally independent of Y, of the potential outcome Y little a, given X, then you can condition on it or not, and it doesn't make a difference, because that's the meaning of that's the definition of the conditional independence. And so we're going to start with this, and we're going to end up with this statement down here, which is precisely the meaning of this. Okay, so is this the case? So this is with the this second statement down here. Is this the case? So on the right-hand side here, we can use total expectation. So we condition additionally on X here. And then we can group some terms. And again, I'm just going to go through this quickly, but you can kind of go through more slowly if you like. So here all I've done is group terms where X is such that they have their share, they have the same propensity score. And then here I can get rid of this because it's not necessary if I've already conditioned on X to condition on a function of X. It's redundant there. And then here I'm just condensing some terms. I pull out a constant because within here this is a constant. So this is this number P. And then on the left-hand side, I'm going to follow a very similar process, but I'm going to leverage some conditional independence, and I get to the same answer. So indeed, these are the same quantity. So again, the bottom line is that the propensity score summarizes all of the confounders into a single number. And what that means in practice is that it suffices to adjust for or match only on the propensity score. So that is the motivation for propensity matching. So if we have here, let's say the situation where there's multiple covariates, and if you were doing covariate matching, you might wonder, okay, can I match this person to this person? Well, their x1 and their x2 are pretty different. So I don't know. And do these people match? Maybe it doesn't look like there's any good matches here. However, if I tell you this function of the covariates is 0.5 for both of these people, for this person it's 0.7, well then I can match these two people together. Because if the propensity scores are the same, then here this conditional mean, this is not I'm abusing notation a little bit. Here mu is this. Here mu is this conditional expectation, y given pi of x a. But certainly this is the case. If pi of xi, even if xi is not the same as xj, well, if pi of xi is the same as pi of xj, certainly these are equal. And then again, from here to here is our identification. So again, here a little bit hand wavy, but hopefully you can follow the gist of the argument that I'm making. And kind of as a corollary to this, you actually, if you're doing a regression adjustment, you also only really need to adjust for the propensity score. You don't need to actually adjust if you believe that you have the right propensity score. Which begs this question: how would we know? How would we know that these people both have propensity of 0.5? You don't know that typically because you usually don't know what this propensity score is unless you're in a randomized trial. But most often you need to estimate the propensity score. So for that you can use logistic regression is very common in epidemiological practice, but there's no reason. I mean, we've been talking about this for a couple of weeks now. There's no reason we have to stick to those more basic methods, and you can use machine learning classifiers to do this as well, because this is just a machine learning problem. Because like I said here, the propensity score is just a conditional mean. It happens to be so for example, if I have little a, if this is 1, then so pi 1, normally when people say propensity score, they mean pi 1, the probability of treatment. Then this is just the expected value of a given x, right? So if I were to do this, for example, with logistic regression, it would just be like GLM a tilde x, and whatever, it could be x1, x2, x3, so on. Data, family equals binomial or whatever. And that's how you would fit your propensity score model from the data that you have. So that's with the kind of basic logistic regression. But like I said, there's no reason that we have to limit ourselves to those methods. You can use the stuff that we talked about in the last lecture and estimate the propensity score non-parametrically as well. So here's an example of doing that. I have this data set. Here, this is actually, I happen to know this is from an RCT, so the true propensity score is actually 0.5 for each person. But what I'm doing is I'm splitting the data up into 10 folds. And the reason for this is that, I don't want to include any person in the data set that is used to train the model that will then predict for that person again. So I'm holding each person out, training a model, and then using that model to predict for that person, and then kind of repeating that process for every person. You can do that exactly if you use this LOO leave one out CV function, but you can do it in chunks, and that's what I'm doing here as well with vfold CV, so I'm doing it in 10 chunks. And within each chunk, what I'm doing is I'm using a random forest. I say mode equals classification because in this setting, basically I want to use a different loss function that is a classification loss and constrain the outputs to be between 0 and 1. That's essentially what this is doing. And then the fitting looks very similar to what we were talking about last lecture. The only thing you should remember is that for tidy models, if you're doing classification, it expects the outcome variable to be a factor. So here in this data set, the outcome variable is 0, 1. And so you have to wrap that in factor just to make it work. But it gives you, if you don't do this, it gives you a very helpful error that basically tells you that you have to do that. And I'm highlighting that I'm fitting the model just on the training part of the data within each fold. And then I predict for the testing fold. And the other thing that you have to do here that is different from the regression setting that we've been talking about is that you have to say in the predict function, similar to when we were doing prediction for GLMs, there were different types of outputs. You could get the output on the kind of a log odd scale, or you could get the output directly in the probability. And it's similar for tidy models. If you have a classification model, you typically want to have type equals prob to get the probabilities out. And then the last little complication is that tidy models actually will give you back a data frame with 2 columns. The probability of that each observation is class 1 and probability of it being class 0. And since there's only 2 classes here, they're going to sum to 1, right? You can get the other from just taking 1 minus the other. But this is because in general, you can actually use these methods in problems where there may be multiple classes, like the outcome could be A, B, or C. And in which case the model would be fitting. What's the probability of it being A? What's the probability of it being B? What's the probability of it being C? And so you would have these outputs, probability A, probability B, probability C. And in tidy models, those are going to be called .pred underscore and then whatever the factor level is. So here I'm getting .pred underscore 1, which is the probability of treatment given these covariates. And you see that is what we get here. And so I've done this, like I said, separately for each fold. And then map underscore df will glue this all together into a single data frame at the end. So as an alternative to matching, which I talked about here, propensity score matching, which is just like covariate matching, except we first boil down all the covariates into a single number, the propensity score. You can also do what is called propensity stratification. And the idea here, there's the math that you can read through, but the idea is this, that within each stratum of the propensity score here, what this statement says is that in each stratum of the propensity score, we have a randomized trial. So what we can do is we can split up our data into the different strata of propensity scores. So we can take all the people who have, that's what kind of this notation means, all the people who have their propensity score about equal to 0.5 and group them all together. And then analyze that data with the naive estimator. So just take a difference in means, because within that stratum, it's a randomized trial. Then we go and find all the people who have propensity score equal to around 0.9, or maybe say 0.9 to 1. So you chunk it into like quantiles or of some kind. So deciles is common, or quintiles people do. And then within each of those chunks, you basically use the naive estimate. So that's what we have here, right? This is essentially the naive estimate, yi given a equals 1 minus yi, the average of yi given a equals 0. But within these strata, and then you just average it, right? So what we're getting is this, which again looks just like the kind of like a identifying estimand, except instead of x here we have pi that we were doing when we were adjusting for covariates directly, and then we're just weighting by the number of people who are in each stratum. So we get all the naive estimates, we aggregate them per stratum, and then we average across the strata. So this is literally the same as if we were doing like a covariate stratified. So we first stratified by, if we had like, let's say 10 different groups of people in terms of their unique covariate values, we stratify, do the ATEs for each of those, and then aggregate. It's just here it's a bit easier, because if we were trying to do this directly on covariates, there would be too many strata, most likely. But if we do it on the propensity score, the one number summary, then there's more likely to be enough people in each stratum that this is a good approach. So that's the propensity score stratification. We did matching. There's also propensity score weighting. And to get to that, you have to understand this other identification result, which is that you can actually get an estimand. We've been working with an identification result that from here, we know that this is equal to this average over these subgroup averages. A comma x. Okay, but it turns out that if you take this a different way, you can get to a different form of the estimand. So this thing that we end up with looks very different than this, but they actually are the same thing, which is interesting. And the way that you get there is kind of similar. You do total expectation first, then you introduce this factor of 1, which is the propensity score over the propensity score. And then here what I'm doing is I am just using the definition of the propensity score, that it's the expectation of this indicator given x on the top. And then here I can actually, since this is independent of this, here I use the identifying assumption. So here this is identification assumption to go into here and combine those two. Because the product of the expectation of two independent random variables is the same as the expectation of the product. And similar for conditioning, you just have to take the conditioning through. And then here, this is for each value of x, this is a fixed number, so you can bring this into the conditioning. And then total expectation the other way to aggregate. And then to here is just the fact that when a equals a, then this ya equals y, if I'm not missing anything. So again, not super important. This is just here for your reference if you're curious. But the reason that this is necessary to know is because this implies a different estimator, a different kind of plugin estimator. So we had our regression plugin estimator, which is you start with this and you go to, we've been looking at this for weeks. The regression plugin estimator looks like this, right? It's based on this identification. But if we use this alternative form, you have this. And here you see there's still, it's a similar problem because you don't know what this function pi a is. Of course, you don't know the expectation too. So here you have to do the sample average to replace the expectation, and then the pi a, you have to put a hat on there. So again, you need some kind of regression estimate of a function. And this is called the, so to get this, you do the regression estimate and then you plug it in, just the same way that we did with the outcome regression, except here the regression is the regression for the treatment mechanism, not for the outcome. This estimator is called inverse probability of treatment weighting, or sometimes Horvitz-Thompson. We would use it in the context of survey sampling. And unlike matching, or sometimes also stratification, you don't throw away some data, because for matching estimators, even for propensity score matching, sometimes there's a person who's kind of too far away in terms of the propensity score in order to be considered a good match. And what is considered a good match is also very hand-wavy and heuristic. So the weighting estimator is quite nice because everyone gets included. Everyone gets a weight. So when I say weight, I mean this number here. So this here I call the weight. And then this is the outcome. So the ATE is just this weighted average of the outcomes, or rather here this is an ATE, but it's the expected outcome had we treated everyone a particular way. This is just a weighted average of the outcomes that we observe in the data. And everyone gets a weight, and everyone gets included with this weighting estimator. Moreover, because this estimator has this nice form where it's just this sample average, oftentimes it's much more amenable to statistical inference than understanding what the sampling distribution of this thing is relative to the matching estimators, where the theory can be quite complex because you have to pair people, and it's very difficult to understand those papers. Now, the intuition here is that, so what are these weights doing? What they are doing is upweighting people who are good representatives of the opposite treatment group. So David Ben-Kessler, who's a professor at Emory, I think, has this nice tweet. He says, okay, so in the observed world, some people are really unlikely to get the treatment. So suppose that in a particular stratum of the population, only 5% of the people get the treatment. In the counterfactual world, everyone is getting the treatment, okay? So what we need is for that one person in our observed data set to represent what would have happened to the other 19 people who are in the same stratum in the same stratum of the population. So we need to upweight them essentially by a factor of 20. Or in other words, and that's what this is doing. So here this is a 1 over, if this number is 5%, 1 over 5% gives you a factor of 20, 1 over 0.05. So you get 20 times their outcome. So that's basically the idea. And you get the other case too. So if you have people who are in a treatment group and they're overrepresenting what would have happened in the counterfactual world, we have to downweight their contribution. So that is what the weights kind of mean. And this is very closely connected to actually the stratification estimator, because if the propensity score has discrete values, so this is the IPTW estimator. We have A over a person's propensity score, and then we're averaging over that's kind of like the weight times the outcome. Well, we can group this. This is a sum over I, but we can group this over the different groups of people who have unique values of P. So let's say there's, P is the propensity score. Let's say there's people who have 0.1, people who have 0.2, people who have 0.5. So there's like 10 different groups, right? So we just group. This is the average, or this is just like the sum of these weighted outcomes, just over the group of people where the propensity score equals 0.1 over the n little p. So p here 0.1. So however many people have propensity score of 0.1, this is the sum of their weighted outcomes. And then we're summing over all of those groups. So, and then here I've introduced a factor of 1. So this is exactly the same as this. I've just broken up the sum, and I've introduced this, I've just multiplied by 1 in here, which does nothing. Now here you notice that within this group, the p is a constant number because everyone has pi equals p. That's also why I was able to replace pi with p. Everyone in this group has this value p, so I can pull the p out as well and put that here, and then I can pull this n in, so I have a np over n, and then here I have a 1 over np times p. And this is how many people are in this group, and this is how many of those have a given treatment. So this is like the total number of people who are in this group with this treatment. And so this thing as a whole is just the sample average outcome of the people who are in this propensity score stratum who are getting treated. And then this is just like a weight of like, okay, how many people are in that stratum relative to the total population, which is exactly what we had here. So it's exactly this, except here I've written it with the A to E, so I have the other term. But if you just ignore that, you have kind of this and this. This is exactly that NP over N, and then this is that sample average within this group. So weighting is kind of like if you take the number of strata to infinity and you kind of very finely stratify everyone. That's the weighting estimator, and it's very, of course, closely related to the stratification estimator, which itself is very closely related to the matching type estimator. So these are all really the same. They're not that different in terms of what is going on under the hood. So the nice thing about these propensity score methods is that they allow for this kind of matching, quote unquote matching, because in the weighting case you're not explicitly matching, but you're kind of implicitly matching actually. So it's this high dimensional matching where you don't have to worry about the dimensionality of the covariates because you've boiled them all down into a single number. The weakness of all these methods is that they do require the good estimation of the propensity score, just the same way that all of our outcome regression methods rely on having a good estimate of the outcome regression. If your outcome regression is misspecified, then you're going to have bias in the estimator. And so this motivates these so-called doubly robust methods. So to kind of compare, we have not shown here are covariate matching methods, which kind of don't work at all in any kind of high dimensional setting. So we say, okay, we can boil that down to just having to do a regression on the outcome or a regression on the propensity score and say, okay, well, over here, we need to do a good job estimating the outcome regression, not misspecify that model. Versus over here, we need to do a good job estimating the propensity score, not misspecify that model. And over here, I say there's bad theory for inference because if you're using arbitrary outcome regression, that not just like linear regression, but things like random forest, without TMLE, you can't really get a confidence interval. Maybe you have to bootstrap. It's a little complicated. However, on the other hand, empirically, there's pretty good performance using these things, even when the model is kind of misspecified. And this is not theoretical. I'm just saying that in a lot of simulation studies, in practice, it just seems like outcome regression is a bit more stable and seems to work well. Whereas for propensity score methods, sometimes they can, like with this weighting estimators, you can actually get some nice theory for inference. Things are ID. The math works out a bit more nicely, but the performance is, even for the matching estimators, you can do this stuff. It's just kind of tricky. The performance, however, in practice is so-so, especially for the weighting estimators, because what you're doing here, if somebody has a propensity score that's very large or very small, that's kind of like saying there's some stratum of the population where the treatment is almost deterministic, or control is almost deterministic. This weight is going to be very, very big. So, for example, if this number is very small, then 1 over that is going to be huge. So some outcomes can get really, really overweighted, and the estimator will be very, very sensitive to values where the propensity score is near 0 or not near 0, and so the variance can actually get really large. And so even if the asymptotic properties of these estimators are nice, the finite sample properties are not so good. Whereas here, the finite sample properties appear to be pretty decent in a lot of simulations, even if the asymptotics are kind of unclear. And so this motivates, ¿por qué no los dos? Is there a way that we can kind of get the best of both worlds? And indeed, that is the case. And this is kind of the most modern way of doing it. This not specifically. Here I'm just giving you like a heuristic idea of what we're trying to do, and then I'll talk about how it actually is done in a theoretically grounded way. But you could imagine that if you just wanted to kind of hand wave combine these methods, one thing that you could do is this. You could first estimate the propensity score. Second, within your buckets of the propensity score, so stratify according to the propensity score, and then do regression models. Because the idea is that, okay, in each propensity stratum, I have essentially a randomized trial already if my propensity score is good. And so I can just take the naive ATE, but you know that in a randomized trial, I could also adjust, and it's not going to hurt me. And I mean, in fact, it's going to reduce my variance, right, of the estimate. So it's actually a good thing to adjust for covariates, do a regression adjustment within a randomized trial, even if I don't have to. So I'm going to do that. But the nice thing of doing that is that actually, even if I'm not in a randomized trial, the fact that I did the regression adjustment means that I can get unbiased estimation, right? So even if I've stratified into the different buckets, and each bucket is not a randomized trial, but it's an observational study instead, the fact that I'm doing regressions means that I can still get back to the causal effect if those outcome regressions are now well specified and are doing a good job at capturing the relationship between the outcome and the covariates. So the intuition here is that if I do a good job with the propensity score, I'm good, because I don't have to worry about the misspecified regressions if in each bucket I basically have an RCT. On the other hand, if I do a bad job with the propensity score, but I do a good job with the regressions, it also doesn't matter, because each bucket is an observational study, but then I'm adjusting away for confounding using the regressions that are good. So I'm good, and if either model is right, I don't need both. I just need one of the two. So that property is called double robustness. So if you have estimators that are okay, that are unbiased, if either of one of two regression models is working well, then they are called doubly robust. So this approach, this is actually, you can theoretically ground this. So this is like with the propensity score stratification, but like the weighting version of that, where you're not throwing away data and don't have to make a lot of ad hoc choices, looks like this. So this is called augmented inverse propensity weighted estimator. And the reason it is called that, well, there's actually two ways to look at this estimator, but one is as an augmented regression estimator, and the other as an augmented weighting estimator. So I'm going to write it the other way so you can see. It just has to do with the terms. So here I could instead write it like this, and then so I'll have a plus. All right, I think this is right. Yeah. So this is the same thing. I just kind of move some terms around. But what I'm trying to show you is that this top estimator is, if you just look at this part, this is the plugin, right? This is the plugin regression estimator. But I've added this other part here, which is this kind of like propensity score weighted thing with the residual of the regression model. So this is like an augmented regression estimator. Down here, if you just look at this part, this is the propensity score weighted estimator. But then I've augmented it with this regression estimator with some kind of like residual-like thing for the propensity score. So this estimator is a combination of the two. You can either see it as an augmentation of the regression estimator or as an augmentation of the propensity score weighting estimator. It's the same estimator either way. Why it takes this form is definitely beyond the scope of this class, but this is a very good estimator for a lot of reasons. And in practice, you actually can implement this yourself because you know how to estimate these regression models. You can do this with tidy models. Just make sure to do cross-fitting. Same thing with here, the propensity score. Just estimate that with cross-fitting. Then just generate all these predictions and then mash it into this formula, and there you get your ATE. So this is also called, sometimes people will say this is the doubly, quote unquote, doubly robust estimator. That's a bit of a misnomer. There are many estimators that are doubly robust. This is, kind of doubly robust in some sense. So this is AIPW, AIPTW, DML, double machine learning, if you are doing the cross-fitting and you're doing machine learning for these functions. All basically the same thing. And the reason why this is nicer than this is because for this, it's well understood that you can actually get the standard error. And again, this is something that you can calculate because here you just put the plugin for the mu a's, you get all the predictions, you mesh it into this, you take the empirical variance of this. So this is like a mutate. If you have your data set, which is like x, a, y, well, you just do mutate to get your mu a's, basically your mu1, mu0. You get a mutate to get your pi1, pi0. Those are all just the cross-fit predictions. And then another mutate to get this term here. And then you just take the variance of that column. And that is your asymptotic variance. You can divide that by n and take the square root of all that to get an asymptotic standard error and build a confidence interval. And indeed, you may recognize this because this is the same variance formula that I showed you last week for the variance of TMLE, targeted maximum likelihood estimation. And that's because these estimators are actually the same in an asymptotic sense. So you can do this, you can do TMLE. This is kind of nice because you can kind of do it yourself. But TMLE is nice because there's a package already for it. So they're actually asymptotically equivalent. TMLE is a little bit better. We'll talk about that in a second. But in large samples, they're going to give you the same answer. And so a little bit of history here. And in terms of what we've been talking about, we've got in the 1980s, people started talking about more seriously about potential outcomes, and propensity score methods kind of came out of that. Regression methods have been around for a long time, but people doing regressions in the 1800s, but they started to be more formally understood also in the context of causal inference in the 70s, 80s or so. A lot of people doing econometrics and things like that. AIPW, I mean, this was actually, I think, the first use of this. I mean, all this stuff actually comes out from much more general, like statistics, like deep statistical theory. But I would say common knowledge of this kind of estimator and applications, or like mid 90s, 2000s, which was also when the machine learning tools started to become incorporated. Previously, it was just logistic linear regression for the most part, or more other bespoke regression methods that were maybe used by statisticians, but not so much in practice. And then this kind of led to TMLE, which TMLE is more closely related to regression methods because it's a plugin. You just have to modify the prediction function a little bit in a special way. But these are very closely related. They're asymptotically equivalent. And I just put this here because this is an absolute like Neanderthal oversimplification of the history of all this. I'm just trying to give you a general idea of what the picture is, so you know where to look. And this is all due to a lot of people. When I talked about the kind of deep underlying theory that is like, okay, well, how do we know that this is the case? How do we know that this is the right thing to be using? A lot of that owes to the work of this guy, Lucien Lecam, who was a statistician here at Berkeley. Surprise, surprise. And then some of this propensity store stuff, a lot of that is due to this guy, Rubin. In fact, sometimes people say the Rubin causal model to refer to the potential outcomes model. Jamie Robbins and Andrea Rudnitsky did a lot of the work in estimating occasions in like AIPW in a more general form at Harvard in the 90s, and going into they're still very active. Jamie is actually a really interesting guy. He had I think he has an undergrad in math, but then he was a doctor, and then he was doing stuff in like labor. Like I think he was doing expert witnessing for people who were injured, had some like work-related injuries or exposures to like chemicals at work, and he was basically trying to get them compensation from the corporations and prove statistically, mathematically, in some way that the outcome that they had suffered, whatever disease, was in fact due to the exposure. And that was his interest in developing all this stuff. But he doesn't have a single, like, he doesn't have a PhD in statistics or anything. And I think he may have even not finished his undergrad. Anyways, crazy guy. Very important. And so this guy here is Mark Vanderlaan, who you may know. He's here at Berkeley, sits upstairs in Berkeley Way West, and he is the founder of TMLE. They worked together. Jamie and Mark in the 2000s wrote a book that kind of summarized this kind of AIPW way of doing things with machine learning. And then at Berkeley, he formalized this TMLE framework. This is somebody who you might also know, Maya Peterson at Berkeley. She's in biostat and also in charge of the computational precision health program. And her papers are great to read if you want to see like really how this stuff meets the road in really important applications. And she also developed I believe the causal inference class that is still taught here, I think now by Laura Balzer. So there's many, many more people that I could have mentioned. I just want to give you a quick sample of some of them, so you know who they are. And in general, people have done a ton of simulations for like all of these kinds of methods, and TMLE is typically best. So here's a bunch of comparisons where they're combining matching type estimators with regression estimators. And here they're doing, TMLE, this is just your plugin, your standard plugin. Naive, yeah, so on and so forth. And you can see that in terms of kind of rankings of mean squared error and bias and variance, TMLE is at the top of the list in terms of these simulations. This is another simulation study where TMLE, if you look in here, has very good coverage, some of the lowest mean squared error across these different. So here, when they say Q correct, G correct, this is are you correctly specifying either model or not? And then here's with machine learning, TMLE. You can see this is the lowest error out of all of these. Another simulation study. The overall picture is, if you're not going to use TMLE, fine. The important thing is to do machine learning. So flexible fitting of either the assignment mechanism, that is the propensity score, or the response surface, or ideally both. And ideally with TMLE, because it does tend to be a little bit better than AIPW.